professor at Unicamp. Most of you, I guess, know him. So please.
So, first of all, I apologize. The kurtosis of the time, arrival time between Campinas and Sao Paulo is very high and positive. It was supposed to be an hour and 10 minutes, and it was 2 hours. Secondly, I really appreciate even more than usual this invitation from outside the field. My collaborator is
Here is all gravity. As long as you do gravity, you are within the field.
fair enough. This is actually something that was an archive very soon. The paper is written, and what poses us is exactly what I'm doing now. I wanted to sort of give a good talk about this, send it to a few people, but it's obviously better. So I will give an introduction. I was hoping to sort of give a broad audience talk. So I will give a longish introduction of dark matter, and then I will try to convince you that there is compelling circumstantial evidence that something like dark matter really exists. And then I'm going to sort of change my mind, because this is sort of the path I follow, and say that the way that general relativity has been expanded so far might not work for a certain very particular set of circumstances, which can be parameterized by a parameter which is small for when post-Newtonian expansions work, but it's different from the parameters which have been used so far. And what is really interesting is that if you actually calculate this parameter, it's big exactly in the situations where dark matter is thought to arise. We have a parameter, we don't have an effect. We need an effect. This is sort of, and we're not experts on this. So this is sort of where we stop. So, I mean, dark matter is, if you go to someone from outside of physics, there is this meme. It's what give physicists a bad name. You do calculations using a non-sophisticated technique and they don't work, and then you add an extra parameter and you write a paper about it. That's not actually true. Because that's not actually true. It's what non-physicists say about physicists. Because the evidence for dark matter, I'm from outside the field, but I do follow the literature, and the evidence from dark matter is extremely compelling. I mean, the classic one that we've known for decades is, of course, galaxy rotation curves. And this is sort of first year undergrounded physics. The virial theorem gives you a relation between kinetic and potential energy, and this way you can calculate the mass density, and you can also calculate the mass density by counting stars and putting them into a mass luminosity diagram, and the two don't match by a factor of 4, especially the outer hollow of the galaxy. So galaxy rotation speeds don't match. Well, maybe gravity works differently in galaxy rotations. Maybe so, and there are people who are working on this, but there is more, because exactly the same deviation from gravity expected from the dark matter hypothesis, in other words, a big mass distribution, shows up in microlensing. I mean, you see distorted images on the sky if you see a galaxy, and these distorted images are consistent with the mass distribution you see here. And in fact, one particular example is something really beautiful that you can sort of really explain it to your grandmother if you work on this stuff, is the bullet cluster. You have two galaxies that collided. They sort of stick together because they interact. If dark matter exists and it only interacts gravitationally, you expect the dark matter not to feel the collision, and the clumps of dark matter to continue going. And if you look at microlensing, this is exactly what happens. You have two sinks in gravitational potential, exactly where you would expect the galaxies to have been if they didn't collide. So this is great. Then there is, of course, the fact that we are here might be thanks to dark matter, because if you look at the standard Big Bang model and you try to simulate structure formation without dark matter, the anisotropies, which you measure from the CND, are simply too small, and they wouldn't have clumped together to form groups of galaxies and galaxies. But if you put in dark matter in about the quantity you observe, you actually get structure formation. So everything checks out. And last but not least, I talked about CND to measure to accurately describe the third peak. I'm mean, the CMB between inflation and recombination also has Newtonian interactions, and they make, you have this Jeans instability, and they make the peaks come closer together, and this is controlled by the third peak, and dark matter works exactly as it should. So you have evidence from galactic scale, you have evidence from sort of around galactic scale and intergalactic structure, you have evidence on far above galactic scale, and you have evidence of cosmological scale, and the evidence is exactly the same. Seems that there's something that has extra attraction and doesn't emit photons, but it interacts very efficiently and it's consistent with sort of heavy particles or primordial black holes or whatever. On the other hand, what is interesting is that most of this evidence comes from either Newtonian theory or Newtonian theory plus light mechanics. Sort of the dynamics is not Einstein, it's Newtonian. We know that that's not really right. I mean, Newton is an approximation to Einstein, and the universe runs on Einsteinian gravity. So could this be a problem? In fact, there is a small community in the literature which publishes papers about this for decades now. I think the Cooper-Stock papers from the early 2000s, where they basically say they take an axially symmetric rotating body and they solve the equations of general relativity, Mathematica does wonders. And what they basically find is that the post-Newtonian expectation completely fails, and it fails by about the amount of dark matter. The first such solution is called Cooper-Stock-2 solution. Sort of the most famous solution is of this type is Balazs and Grumiller, and recently there was this effort, which is a sort of much more realistic, of Galoppo, Wiltshire, and Emanuele. Well, he might be here. Galoppo and Wiltshire are my co-authors. I mean, basically, what happens that I've stolen Marco Galoppo's talk here, is that small metric perturbations around Minkowski space is not the same thing as small metric perturbations. Is not the same thing as the metric that has all the symmetries of an axially rotating body. And the commutation between them, not quantum commutation, but commutation of different approximations, gives you this, what they call quasi-local angular momentum.
What is EFE?
EFE, that is the effective, honestly, good question. I think field expansion. Yeah, or something like that. No, it's not the. I said I stole this slide. I didn't make it.
Could be Einstein field equation.
Yes, thank you. It's the Einstein field equations. Yeah. So basically, what he's saying is expanding around Minkowski and solving general relativity as an expansion around Minkowski and expanding around the axisymmetric rotation and then doing the Taylor expansion doesn't commute. And the order of the non-commutation, there's these funny new terms which have to do with angular momentum. This would be one of the crucial points. Are actually of the order of the dark matter. What we mean by dark matter. And this is just general relativity. There is no Mach, there is no extra stuff. It's Einstein's equations with ordinary. So basically this name would be true. We solved GR incorrectly, yes.
But you haven't told us what is the small parameter. So angular momentum and dimensions, no? So what is the parameter actually?
Momentum doesn't have dimensions, it's position times momentum.
No, come on, you don't have H bar.
H bar is one. I will.
Then it's back to the 100.
Yeah.
Then it's short.
I will talk about this.
Okay.
I will. It's a good question, and in fact, my talk sort of gives one answer to this.
Okay.
Yeah, but I mean, they call it the quasi-local angular momentum, and for those, I will come back to this. For those who Defining angular momentum in general relativity is something that people like Yao of Calabi-Yau manifolds work on. It's still haven't resolved. I think he says he resolved it, but yeah, it's not but it has to do with angular momentum. Yes.
Going back to the slide that you had, like the perturbation one, is it like assuming some care-like metric and doing perturbations on top of that, or like this axis symmetric?
Yeah.
Thing? So you are doing why the perturbations of top of like the care-like thing? Because like how can I imagine doing the physical mapping of plating galaxy with respect to the ansatz of the intrinsic metric plus perturbations that you are putting here?
No, I mean, they don't perturb. The perturbations in these two mean different things.
Yeah.
So it's not surprising that they.
So I want to understand the perturbations in the second.
Yeah, so here perturbations are simply, the expansion in H and V, but after you impose that axis symmetry. Here, first you expand in fields and then you impose the axis. These are the procedures.
Okay.
Yeah. So the mean is correct. We've calculated incorrectly and then we've invented a dark number to fix the error, right? Well, no one believes them. I mean, if you look at the papers that cite, Cooper-Stock and Tube, Balazs, Miller, etc., there is a lot of comment on papers. I mean, and it's actually a nice exercise to go to the literature because the arguments are sort of difficult. I mean, at least they're difficult for me. Why? Well, first of all, these solutions are certainly naive, even the more realistic ones. I mean, the Cooper-Stock and Tube has a disk singularity, for heaven's sake, with all the galaxy. Balazs and Miller, I think, is rigid. Yeah. So these are not physical solutions, they're toy models. Sort of, but they might be good enough to show that the symmetry issue is not trivial. And this is the big point. In GR, it's also very easy to get confused between having the wrong solution and looking at the correct solution in the wrong coordinates. Many of you will do this stuff, and there have been people who basically say that you're choosing a weird coordinate system because that's where you can solve, and that's your thing. And thirdly, I mean, I went through the evidence of dark matter because I want to show that it's not just galaxy. They just answered galaxy rotation theorems, but then the evidence for dark matter is much more than this. It's microwave thing. I mean, now they're starting to look at lensing, but it's this bullet cluster. It's, the CMB and so on and so forth. And most importantly, I mean, Taylor expansion is not an opinion, right? I mean, we have the worldwide expert here with pulsars. Taylor expansion work to post-Newtonian effective theory works to enormously high precision, and we have experimental evidence for this. The hierarchy is very well built. You have the metric corrections to Minkowski metric are smaller than 1, velocities are small, gravimagnetic effects are smaller, they're smaller than Taylor expand. And you get the right experimental results. And why should I believe a toy model rather than an effective theory, which is something we've been doing for ages and lots of situations? Effective theory is at the moment the dominant branch of field theory, either classical or quantum. So what gives? I mean, what is effective theory anyway? Well, you identify the symmetries of the system, and here I don't mean the symmetries of the solution, I mean the symmetries of the dynamics, the symmetries of the Lagrangian. You write down all elements of the Lagrangian allowed by symmetries, and usually they're infinite, especially if you're sort of part of the system. And then you identify some small parameter, and typically the small parameter is some sort of scale separation, and order terms by powers of the small. And then the remaining coefficients are sort of all of order 1 by naturalness, and then you can sort of play it sort of, and see what happens. It's associated with sort of Steven Weinberg and such, and so it is because the quantum expansion of it was done by him. But something similar was actually done also for classical physics and also in the 19th century, because there is also even a theorem, a very general theorem called Buckingham's pi theorem, that basically says that wherever you have an equation, you have to find a small dimensionless parameter, and an approximation is what the small dimensional parameter is, either very small or very large. And in fluid mechanics, I mean, there's this nice entry. You have everybody has heard of the Reynolds number, but essentially for fluid mechanics, which is the original field theory, you have an enormous amount of dimensionless numbers which parameterize good effective theories and bad effective theories and regimes. That's what it is. And usually it's a very good approach. I mean, again, what's wrong with Taylor expansion? The point is that no one said it works every time. And in fact, there is this very nice conference proceeding by one of the world's greatest effective field theorists, which sort of explains this very well. There are many scales that interfere, the effective expansion sometimes fails. Asymptotic configurations could make effective theories fail. And here, and this is important for this angular momentum issue, because angular momentum presupposes boundary conditions which are different from zero angular momentum boundary conditions. And finally, a really important thing is that we usually in effective field theories, either sort of the fundamental, the better theory, if you want, is more symmetric than the effective theory, or they have the same symmetries. It almost never happens that the fundamental theory is less symmetric than the effective theory. The thing is that there is no real scientific principle as to why should not this be true, especially if we consider that by the useful symmetries for equations of motion are global symmetries, because Noether's theorem tells you that a global theory is a conservation law. So is general relativity more symmetric than Newtonian gravity? Yes, if you consider sort of local symmetries, or it's sort of the same if you consider that Newtonian theory has the equivalence principle, but on the other hand, general relativity has its sort of built in. But no, if you consider global symmetry, for example, Newtonian gravity conserves angular momentum. General relativity, it's not even well defined. There is arguments in the mathematics literature about what the global definition of angular momentum is. And all of these solutions that deviate from Newtonian limits involve asymptotic frame dragging, which is what violates angular.
I don't quite agree with that.
Well,
Well, in which sense the general relativity does not concern angular momentum?
in full general relativity.
Yeah, but locally it does.
Locally it does, yeah, but the equations of motion, if you sort of look at the system which is rotating, you know.
No, but for astrophysical system they do.
Yeah, well, for astrophysical systems where tides are of the order of angular momentum size, they don't. This is sort of the crucial point that we're talking about. If curvature changes over where angular momentum is defined, angular momentum is defined as distance times perpendicular velocity. If you have big curvature gradients at that distance, I don't know how to define local momentum. And that's the point. Angular momentum is generally not a local one.
No, that's very sure, no, and you need some asymptotic flatness to define each other. I mean, sure.
All right, sure.
So if you have this asymptotic flatness, it would be a quantity that you could define and somehow be some gauge invariant thing, or not?
There is none. The quasi-local angular momentum is sort of quasi-conserved. But there is no real conservation equations. I mean, my co-author is ashamed that my co-author knows a lot more about than me. And then when you ask, so what do you mean exactly? And it turns out there are several definitions of possible. It's a technical sort of approach. Yeah, which for what I'm presenting, you do not have to understand in detail, which is nice. All that you have to understand is that what is usually called angular momentum conservation. Because the point is, and this is one of Donohue's big points, if you have a conservation law, which is valid in the infrared, but not valid in ultraviolet, even if you have big scale separations, effective expected expansion effect independently of the scales. The basic reason is, I mean, so why does perturbation theory work at all? There is this very general theorem called Kolmogorov-Moser that basically says that if you have an integrable system and you perturb it a little bit, almost always there is a gap, which is sort of these inner circles, and other than exact trajectories, which are sort of integer multiples, so they're very unlikely for initial conditions, the perturbative expansion will The thing is that the size of this gap is inversely proportional to the degrees of freedom. Which is actually one of the reasons, which is why we can't have nice things. We can't have thermonuclear energy, because the Vlasov equation that governs the whole plasma is very, very unstable. And this is something that for the Vlasov equation, this gap still exists, but it goes down to zero. I mean, it's the number of degrees of freedom. So for many bodies, an arbitrarily small perturbation, you can also see this here. I mean, these filaments are instabilities. That's what they are. So for many bodies, a small violation of conservation law means that the system goes from integral to non-integrable, and then the small corrections would basically be done. This is sort of our quantity of choice is angular momentum. Why? Because I should say that if the metric depends on time and if the metric is highly asymmetric, basically all conservation laws are only well-defined globally. Globally, they're all violated. Angular momentum is special because angular momentum is also not defined locally. It's defined locally. And in general, you have big curvature gradients over the loops. And if this happens, and also if you have many degrees of freedom, the post-Newtonian expansion might be suspicious. And this is important because for pulsars, for where post-Newtonian expansion has been applied successfully, you don't have many degrees. But for galaxies, you have 100 billion, well, 100 billion atoms, right? I mean, suns.
So,
yes.
one question there. So somehow that means that the normal way in which you would do perturbation theory in that sense would not be valid. So you could see that higher terms start to be significant at some order,
or it would just completely diverge.
Okay. But then one can actually go to this expansion and measure what's the behavior of those coefficients. And I mean, has this been? Okay.
Last slide. Second, no. Towards the conclusion of the talk, yes. Yeah. So I'm not just to tell you, I'm not a general relativist. I mostly come from a QCD background. So everybody knows that QCD is hard and QCD is strongly coupled. I mean, this is where we should be about coupling. I mean, I just want to spend a few slides about this. How much time do I have?
Half an hour more.
Okay. So why is QCD hard? Because it's strongly coupled. But coupling depends on the scale. So it's a little bit of a cop-out because, for instance, thermal QCD is infrared divergent at any scale. You can show very easily that infinite temperature QCD is still confining. Yeah. That hard and soft processes don't factorize. You have many scales. In general, if you have many scales, even if the closest scale is perturbative, the overall evolution might not be. The real issue with QCD is that for electromagnetism, if you ask, well, I have two potentials, are they simply engaged in conservation of each other, or is it something more complicated? It's a very easy problem. You basically take these two configurations and you take the difference and then you sort of construct a theta that minimizes the difference. And if this A rest goes to zero, then it's just a gauge difference. And if it doesn't, it's two different field configurations, not just two different gauge configurations. In QCD, it turns out that this is an impossible problem because there are there is this in any non-abelian theory. Because there are because if you have an internal symmetry where you can twist things around, the difference becomes a nonlinear function, which typically has an infinite number of solutions, very complicated solutions. This is known as the Gribov problem, and in a very hand-waving way, this is what results in confinement. That in the infrared gauge non-singlet configurations start being dominated by noise, started by quantum. This is quantum. There is some similarity with turbulence, with hydrodynamic turbulence, because again, you have many solutions which are sort of arbitrarily close to each other, and let's say the very nature of this. So what is the effective theory of QCD? Well, one of them is to assume that at long distances you just have color neutral objects, and this is very successful. This is the theory of Hartmann, pions, protons, etc., etc. Close to confinement sort of breaks apart, and also you cannot, by definition, study confinement. The other effective theory is what people know as the lattice. It's also an effective theory. It's built out of non-local objects. You have a Lagrangian. The Lagrangian is not really computable analytic. The partition. You have a partition function. I should say it's a quantum. It's not computable analytically, but you can run your computer long enough, and you can expand it with some loops, and you have a bunch of coefficients. And so lattice people work with this. What are Wilson loops are basically very similar mathematically to angular momentum. Instead of being momentum, but sort of field, it's vector. Of course, general relativity is not confining. There are actually papers in the literature from that field which basically say it is, but I don't believe them. Yeah. However, this gauge ambiguity and angular momentum non-conservation are an issue. And what this means is that this coarse grading, it might be interesting to invent a coarse grading parameter which has the role of the Wilson loop in QC. So play with it. As I said, this thing is very similar to angular momentum, so it's sort of a guide. In a many-body system, I mean, the point is that this is still a field theory, because for a many-body system, what happens for a fluid and whatever, you have Kelvin's theorem. Instead of having fields at points, you have fields at paths. Instead of parameterizing space in terms of points, you parameterize space in terms of all contours. In terms of all contours that you can draw, and if you have angular momentum, or if you have these Wilson loops, this is actually associated with conservation, called Gauss's theory, and an angular momentum quasi-conservation. And that's general relativistic violations. So summarizing, the weak field expansion could fail if you have these two conditions: significant angular momentum and many body systems. And to see that it fails or not, we have to invent a small parameter. We have to invent a dimensional parameter which has to do with integrals of circulation. It has to be dimensionless. It has to be non-scalar. It has to be non-extensive. And it has to be related to angular. What kind of parameter does it have? Yeah, non-extensive meaning curvature gradient. For the first few weeks, we tried to play with something like this, with 1 unit of angular momentum. And basically, it's not really clear what the quantity of the power. There are two problems. The first one is that it's not clearly related to the conserved angular momentum, because the mu contracts the Riemann tensor. It doesn't contract the angular momentum. And if you look at the symmetries of the problem, if you try to do it the other way, it will be identically zero. So it goes angular, yeah.
J is the angular momentum tensor?
Yeah.
Why the indices?
Because it's XP minus dx.
Fine, that should be 2. Okay. Yeah. No. So the three-dimensional angular momentum, you have to put 1 to 0, 1 index to 0.
Yeah.
Okay.
Yeah, exactly. Yeah. Which I do by contracting a volume element. D sigma,
Yes.
what D sigma is that in its in its homomorphic frame, the sigma is simply devolving a bunch of zeros. So you have to contract the matrix. So there is no connection to a conservation law because you don't contract with the volume, you contract with the R. If you were to contract with J, you would get 0. And also, we couldn't think of the unit of a good unit of mass. However, if you try to do not one angular momentum, but two, if you want the interaction between two Wilson loops, so there's this UCD intuition, something very nice comes out, which seems to have the right properties. It's actually a conserved quantity if there is no approach. It's basically, you take two angular momentums, you contract with two volumes, and then the rest of the indices you expand over curvature, and you have two units of, positive units of mass left, and you put in G, because this is the fear of the Newton's constant. It is not a physical quantity. It, in fact, mixes apples and oranges because angular momentum is sort of defined in the Newtonian theory. Curvature is defined in the Einsteinian theory. This is a parameter that, if this parameter is small, you expect that it's conserved. It's conserved for Newtonian evolution. If this parameter is small, we expect to. If this parameter is small, we expect to the non-local post-Newtonian expansion to work. This is the idea. Now, regarding the units of angular momentum, doing galaxies in terms of h bar, maybe units of h bar is probably not the best thing. Sort of the natural unit that we're using, I mean, galaxies are made of stars, so sort of the h bar is the equivalent where 1 degree of freedom, if you want, is solar mass. So the units in which we're going to calculate is G times solar mass squared. Because we're coarse graining on a stellar size. The analogy with QCD is that in the strong to weak coupling limit, essentially on the lattice, if space-time was discrete, in a strong field where perturbation theory works, the Wilson loop is a perimeter. In the weak field where perturbation theory works, Wilson loop is a perimeter. In the strong field, the Wilson loop is an area, and you can develop it by space. So this is an expansion around this Wilson stuff. It's sort of will be equivalent around an expansion of these other things. And we are kind of expecting that corrections to the virial theorem will be in order of this alpha. So the nice thing is that this is calculable provided you have the curvature, you have a good estimate for the curvature, you have a good estimate for the energy momentum tensor, and you also have a good estimate for the velocity of every volume. Which is where my friends who do these galactic solutions, who also know a lot about galaxies, have no problem with the calculations. We do use a post-Newtonian cylindrical metric, which is gradient. It's standard. We use an ideal fluid ansatz for the energy momentum tensor. And then we have a co-moving, and then we sort of a co-moving volume defined this way. So assume axis. And here comes the thing that got us really excited. We've calculated this alpha in units of GM squared. And for stellar and pulsar binaries, it's tiny. It's completely tiny. For globular clusters, which people tell me one of the issues of dark matter research is that globular clusters don't particularly, that don't seem to have much dark matter. For globular clusters, it's also tiny. It's of the order of the pulsar binary. So the point here isn't just, you're just counting the number of stars. No, you're counting the number of stars, normalizing them by angular momentum over the scale of the curvature. This is what this parameter does. And it does this with how is angular momentum defined? It's you take one volume element, you define the angular momentum by another volume element, and then you integrate over all possible pairs of volume elements. This is what we're doing. And this quantity is tiny for stellar binaries, pulsar binaries, and globular clusters, which have no the order of the 100,000 stars. But for this galaxies is huge. And this is extremely preliminary. They sent me this yesterday, but I will just mention this. I do not exactly know the details of how they calculated it. They've also calculated it for Lagrangian, the local galaxies. And it turns out that it's also huge. I'm not surprised. It's big bodies which sort of move around at high velocities. I mean, this is from observational. I think that this galaxy was from the parameters of their solution, and Lagrangian was purely observing data which we got. So this is extremely encouraging. Essentially, this parameter that we invented is very small in situations where post-Newtonian expansion works, and very large where dark matter is needed. So what does this mean? Well, we don't know how to go further from this because we don't have an effective theory. We just say, here is a parameter that a non-local parameter where post-Newtonian expansion might fail if this parameter is big, even if the field is very weak and velocities are really small. This is all that we're saying. This is the whole claim that we're making. We have this parameter, which is non-local. It could be, it's not a simple matter of counting density of things. And it could be big, even if, yeah.
The effective theory would be then obtained by an expansion of all that parameter.
Hopefully,
And it should agree with general relativity.
and it should agree with general relativity, yes. Hopefully, yeah. And so we do not actually know if this is the solution of the dark matter problem. We just simply say that in these situations, dark matter doesn't work. However, I mean, the beginning of an effective theory is these papers here, which were the basis of what they're doing in this presentation. And indeed, they actually, I mean, they've already done this, and they find that indeed quasi-local angular momentum is comparable to the effect of quasi-local angular momentum is not small. However, this isn't an effective theory because my definition of effective theory was take the symmetries of the system. They took the symmetries of the solution. So this is not quite an effective theory. Sort of says, but maybe an effective theory. So at the moment, we want a Lagrangian, which you can expand in J and alpha. An effective Lagrangian that can expand in J and alpha. I am certainly kind of clueless as to how to derive one, which is one of the reasons I went to the experts of post-Newtonian expansion, such as Unicamp.
Yeah. Here, there's no alpha in the equation. Where is alpha?
No, here, this was done before alpha was invented.
Okay.
Yeah, this is simply, and this depends on the solution. It's not an effective Lagrangian, it's an expansion of the axisymmetric solution in terms of smaller losses. That's what happens. There is no alpha there. One would try to rewrite it in terms of alpha. However, there are a couple of things that I could say. We have absolutely no quarrel with the people who use post-Newtonian expansion to calculate gravitational waves from like pairs of black holes or pairs of pulsars and pairs of whatever, because alpha calculated for such pairs is tiny. Because we need high angular momentum, but we also need extended bodies. It's not just the delta functions. And you can show that it's tiny. Yeah. So the post-Newtonian effective theory should work if either you have few bodies or you have little angular momentum. Post-Newtonian expansion is safe. You need both for this parameter to be big. However, galaxy rotation fails. The bullet cluster also fails because the bullet cluster is two clusters which collide. This is a finite impact parameter situation. So angular momentum of this collision is it's on the order of the galaxy. These are clusters, but they're not normal clusters because they're rotating with percentage. I mean, we haven't found in the literature the ingredients to calculate alpha for the bullet cluster, but it should be much bigger than alpha for clusters in general. And finally, what is alpha of the universe? In the models which were used to explain this, so in lambda CDM and whatnot, angular momentum is basically zero. So alpha for the universe should be small. There should be no angular momentum. However, the reason for this is basically because people like one-dimensional equations. And the model in one dimension works, and there's no data that says something else is needed, so let's go with it. In fact, and here I'm not really an expert on this, again, for the nth time, but there is one thing that I know, that there is evidence that there are magnetic fields on basically cosmological scales, certainly larger than extragalactic scales. And there are quite a few papers trying to explain it. There are explanations, like inflationary dynamics could in principle produce large magnetic fields in the scale of the universe.
But
Yes.
you would need that to also be important quantity on the early universe, and I guess at the scale of like a Hubble distance. But I guess that these magnetic fields in this early universe, I mean, I don't know about that, but you need this kind of coiling effects for amplifying them until the levels that you saw them after.
I'm not really interested in the magnetic fields themselves or what produces them. All that I want to say is that if magnetic fields exist, angular momentum. They're just physics.
Yeah, but
So if there are significant electromagnetic field, there are significant magnetic field, there's significant.
But you would need them to hold until a scale similar to like I don't know what scale, but I guess that should be like observable universe size.
No. You don't need magnetic fields. You need angular momentum to be present.
Yes.
Scale. And to produce magnetic fields are produced by angular momentum. I mean, obviously, in a hot plasma, there are no magnetic fields because of bispring concession.
So what I was trying to say is that in somehow, like what you would need is that at very large scales, like observable universe kinds of scales in the early universe, you would have some kind of you would break isotropy because you would need some angular momentum.
You would need an axial, yeah, you would need a quantity which.
So somehow you would be already at the scale of lambda CDM, breaking directly the isotropy assumption. I don't know what mechanism would claim that, but would already be saying that lambda CDM is not a good proxy in some sense of some isotropy, not isotropic term.
Yeah.
Okay.
Yeah,
I mean,
yeah.
it's fine. At least
Yeah,
theoretically, it's clear.
Yeah, sure, yeah. I mean, you need angular momentum that creates magnetic fields of cosmology. There are proposals, but basically, yeah, you're right. Whatever creates angular momentum automatically has to transform as an axial vector. So, I mean, sort of, this is the conclusion. I mean, certainly, I don't. What we're saying is that there could be this non-local parameter that makes general relativity post-Newtonian expansion go awry, even if the usual parameters like field and velocities are small. And what is really funny is that if you actually try to define and calculate this parameter, it's big exactly where dark matter is needed, except for this early universe, which is a bit more converted, but would be magnetic fields or something like that. So, I mean, the next step would be a post-Newtonian expansion in terms of this non-local parameter, and we sort of do not know how to calculate this, but it's a step. Thank you very much.
Less controversial than expected. Okay, so I would like, maybe I can ask you about you later, but can you just catch on the black or like words, whatever, how this alpha parameter, it has to, it's related to the curvature of the system. I don't understand where the number of atoms enter.
So this is one volume. This is another volume. There is curvature here. You calculate angular momentum of this guy, that guy. And you contract this for curvature.
Okay, so you have one power of curvature and two power of momentum.
Exactly. And then you integrate over all possible pairs of atoms.
Ah, okay.
They normalize each other.
That's where the number of atoms comes in. You have to square.
It does diverge very fast. But originally, I really wanted something that is linear and non-quadratic. By inspection, it turns out that this is impossible. This parameter is either 0 or dimension, and not related to.
Yeah, it's very hard to be this relatively with this many bodies.
I know. Yeah.
So in this case, I guess that for having a big quantity about this alpha parameter, curvature around the volume in which we're computing needs to amount to some, I mean, to contribute. No?
Yes.
So I'm surprised a bit in the regime of like clusters or something. Like intuitively, I wouldn't think them as a strong curvature systems. I would be more like if you are talking about neutron merging or such, I would expect big, huge curvatures. But at the galactic level, it's not a thing that for me intuitively would play.
Very large. You mean like IKEA? Or you
No, like clusters, like,
star clusters?
yeah, like at the globular cluster level, maybe.
Well, at global cluster level.
Ah, because
is
it's
small.
in that case, okay.
Yeah, global
Yeah.
cluster level alpha is really small. Absolutely.
Yeah. So then at the operational level, you would like to build some effective Lagrangian that contains this J with the alpha parameter and do an expansion upon these terms.
At the moment, I would like to convince people that this is necessary. And then either we or someone else can build it. At the moment, the point is that maybe this is necessary. But there are people also who work on.
Zoom is open, but I don't know if anybody can use it.
Maybe somebody is, oh, there are people, there are 5.
Okay.
Yeah, there's people asking if something is happening.
Yes, if people on Zoom want to ask questions, just open your microphone and say. Okay. So, we don't know further question, we can go to the sandwiches, but not before having that Giorgio.
Yeah. I don't know if this happening, this is. Wait for it ready, after what we do like that. Either it will be nonsense and someone can tell us it's nonsense because X, or it requires a lot of development.
No, it's good on these things with preservation, like well, post-Newtonian or particular theory, but I mean, at least from the talk, I mean, it's